Welcome to What If Lab. Today, we're exploring mind-bending scientific paradoxes and logical experiments. What if time travel is possible, or a cat can be both alive and dead? Join us as we uncover 7 theories that challenge reality. Let's dive into the Stanford Prison Experiment, a groundbreaking study in psychology conducted in 1971 by Philip Zimbardo. The goal of this experiment was to explore how situational factors and assigned roles can influence human behavior, particularly in a prison environment. Zimbardo wanted to understand the psychological effects of power dynamics between those in authority and those who are not. What happens when ordinary people are placed in positions of power? How does this affect their behavior and morality? This experiment would reveal shocking insights into the darker side of human nature and the potential for cruelty when individuals are given authority. Now let's take a closer look at how this fascinating experiment was conducted. Methodology. The Stanford Prison Experiment began with the recruitment of college students from the local area. Zimbardo advertised for volunteers who were physically and psychologically healthy, promising them payment for their participation. Once selected, the participants were randomly assigned to 2 roles, guards and prisoners. This random assignment was crucial, as it helped eliminate pre-existing biases and ensured that any observed behaviors were a result of the assigned roles, not individual personalities. The prison was set up in the basement of the Stanford Psychology Department, complete with cells, a control room, and a solitary confinement area. The guards were given uniforms, reflective sunglasses, and wooden batons to assert their authority. In contrast, the prisoners wore simple smocks, were assigned numbers instead of names, and were stripped of their personal identities. The experiment was designed to last 2 weeks, with the intention of observing the interactions between the guards and prisoners in this controlled environment. However, the setup itself created a powerful dynamic that would soon spiral out of control. Now, let's see how the experiment unfolded and the behaviors that emerged. Course of the experiment. As the experiment began, the initial interactions between the guards and prisoners were relatively calm. However, it didn't take long for the power dynamics to shift dramatically. In the first few days, the guards started to embrace their roles with surprising enthusiasm. They began to enforce arbitrary rules and create a strict hierarchy. They used psychological tactics to manipulate the prisoners, often humiliating them and asserting their dominance. The guards would call the prisoners by their numbers rather than their names, stripping them of their identities. As tensions escalated, the prisoners began to exhibit signs of stress and rebellion. Some attempted to resist the guards' authority, which only led to harsher punishments. The guards responded with increasingly brutal measures, including sleep deprivation and humiliation. By the end of the first week, the situation had deteriorated significantly. The prisoners were experiencing severe emotional distress, while the guards became increasingly sadistic. This rapid transformation highlighted how quickly ordinary individuals could adopt extreme behaviors when placed in positions of power. The experiment was revealing disturbing truths about human nature and the influence of situational factors. As we move to the next section, we'll discuss the reasons behind the experiment's abrupt termination. Termination of the experiment. The Stanford Prison Experiment was initially designed to last 2 weeks, but it was abruptly terminated after just 6 days. The decision to end the experiment came when Christina Maslach, a graduate student who visited the prison, expressed her horror at the conditions and the psychological abuse taking place. By this point, the situation had become untenable. The emotional and psychological toll on the prisoners was severe. Many were showing signs of extreme stress, anxiety, and emotional breakdowns. Some prisoners had to be released early due to their deteriorating mental health. Zimbardo himself began to realize that he was losing objectivity as he had become deeply involved in his role as the prison superintendent. the ethical implications of the experiment were becoming increasingly apparent, raising concerns about the well-being of the participants. Ultimately, the decision to terminate the experiment underscored the dangers of unchecked authority and the potential for abuse in controlled environments. It prompted significant discussions about ethics in psychological research, leading to more stringent guidelines in the field. Now, let's explore the conclusions drawn from this experiment and its lasting impact on our understanding of human behavior. Conclusions. The Stanford Prison Experiment yielded profound insights into human behavior and the nature of authority. One of the key findings was the powerful influence of situational factors on individual actions. The participants, who were ordinary college students, transformed dramatically based on their assigned roles as guards or prisoners. The experiment demonstrated that people could engage in cruel and abusive behavior when placed in positions of power, even when they would not normally act this way in everyday life. It highlighted the ease with which individuals can conform to social roles and expectations, often at the expense of their morals and ethics. Moreover, the findings raised critical ethical questions regarding psychological research. The distress experienced by participants led to a reevaluation of the ethical standards in conducting experiments involving human subjects. Researchers are now required to prioritize participant well-being and informed consent more rigorously. The Stanford Prison Experiment remains a powerful reminder of the complexities of human nature and the thin line between good and evil. It prompts us to reflect on our own behavior in situations of authority and the potential consequences of power dynamics in society. The liar paradox is a fascinating and perplexing concept in logic and philosophy. At its core, it revolves around a simple yet profound statement. This statement is false. This paradox challenges our understanding of truth and falsity, as it creates a self-referential loop. If the statement is true, then it must be false, but if it is false, then it must be true. This inherent contradiction raises important questions about the nature of truth and the limits of language. The significance of the liar paradox extends beyond mere wordplay. It has profound implications for theories of truth, self-reference, and the foundations of logic itself. As we explore this paradox, we will uncover its complexities, examples, and the consequences it holds for philosophical thought. Now let's delve deeper into the explanation of the paradox and its intriguing characteristics. Explanation of the paradox. The liar paradox is best illustrated by the statement, "This statement is false." When we analyze this assertion, we encounter a logical conundrum. If the statement is true, then it must be false, as it claims. Conversely, if it is false, then it must be true. This paradox arises from self-reference, where the statement refers to itself in a way that creates a circular contradiction. It challenges our conventional understanding of truth, as it seems to defy the basic principles of logical consistency. To further grasp the implications, consider the broader context of truth in language. Traditional logic operates on the premise that a statement must either be true or false. However, the liar paradox disrupts this binary framework, forcing us to reconsider how we define truth and falsity. Ultimately, the liar paradox serves as a powerful reminder of the complexities inherent in language and logic, prompting deeper exploration into the foundations of philosophical thought. Now, let's look at some examples of the paradox to illustrate its nuances. Examples of the paradox. To better understand the liar paradox, let's explore a few classic examples that illustrate its complexities. The standard example, the statement, "This statement is false," is the most straightforward representation of the paradox. If the statement is true, then it must be false, but if it is false, then it must be true. This creates a loop that defies resolution. The Epimenides paradox. named after the ancient Greek philosopher Epimenides, who famously stated, "All Cretans are liars." As a Cretan himself, if his statement is true, then he is lying, which means it cannot be true. This paradox highlights the complications of self-reference and cultural context. The barber paradox. This paradox involves a barber who shaves all those who do not shave themselves. The question arises, does the barber shave himself? If he does, he must not shave himself. If he doesn't, then he must shave himself. This creates a similar contradiction to the liar paradox. These examples showcase the fundamental issues related to self-reference and truth. They challenge our understanding of logical consistency and force us to confront the limitations of language. Next, we will discuss the consequences of the liar paradox for logic and its implications in philosophical discourse. Consequences for logic. The liar paradox has significant implications for the field of logic, particularly concerning theories of truth and the principles that govern logical reasoning. Challenges to classical logic. The paradox forces us to reconsider the binary nature of truth in classical logic, where statements are either true or false. The liar paradox introduces ambiguity, suggesting that some statements may not fit neatly into these categories. This has led to the exploration of alternative logical systems, such as paraconsistent logic, which allows for contradictions without collapsing into triviality. Theories of truth. The liar paradox has prompted the development of various theories of truth. For instance, the deflationary theory posits that asserting a statement is true is merely a way of asserting the statement itself, avoiding the complexities of self-reference. In contrast, semantic theories attempt to define truth in a way that accommodates self-referential statements, often leading to more complex frameworks. Impact on formal systems. The paradox also highlights limitations in formal systems, such as those described by Gödel's incompleteness theorems. These theorems demonstrate that within any sufficiently powerful logical system, there are true statements that cannot be proven within that system. The liar paradox serves as a prime example of such statements, illustrating the inherent limitations of formal logic. Philosophical implications. Beyond logic, the liar paradox raises profound philosophical questions about the nature of truth, language, and meaning. It challenges our understanding of how we communicate and the assumptions we make about statements and their truth values. In summary, the liar paradox not only disrupts our understanding of truth, but also prompts a reevaluation of the foundational principles of logic. Next, we will explore the philosophical aspects that arise from this paradox and their broader implications. Philosophical aspects. The liar paradox provokes deep philosophical questions that extend beyond mere logical analysis, touching on fundamental concepts of truth, language, and self-reference, nature of truth. The paradox invites us to reconsider what we mean by truth. If a statement can be both true and false simultaneously, we must question the consistency of our definitions. This has led to various philosophical discussions about the relativism of truth and whether it can be absolute. Self-reference. The liar paradox is a striking example of self-reference, where a statement refers to itself in a way that creates contradictions. This raises questions about the limits of language and our ability to express thoughts without ambiguity. Philosophers have explored how self-referential statements challenge our understanding of meaning and interpretation. Infinite regress. The paradox also brings forth the issue of infinite regress in reasoning. If every truth claim can be called into question through self-reference, it leads to an endless cycle of justifications. This has implications for epistemology, the study of knowledge, as it challenges our ability to establish foundational beliefs. Ethical considerations. The liar paradox can even extend into ethical discussions. It prompts inquiries into the nature of honesty and deception. If statements about truth can be inherently contradictory, what does that mean for our moral obligations regarding truth-telling? Impact on philosophical discourse. Ultimately, the liar paradox has sparked ongoing debates in philosophy, influencing various schools of thought, including pragmatism, existentialism, and analytic philosophy. It serves as a touchstone for discussions about the complexities of human language and thought. In conclusion, the philosophical implications of the liar paradox are vast and multifaceted, challenging our understanding of truth and prompting us to reflect on the nature of reality itself. Next, we will summarize our exploration of this intriguing paradox and its significance. Conclusion: the liar paradox stands as one of the most intriguing and perplexing challenges in both logic and philosophy. Through our exploration, we have seen how a seemingly simple statement, "This statement is false," can unravel complex issues about truth, self-reference, and the nature of language. We examined how the paradox disrupts conventional binary notions of truth, prompting the development of alternative logical frameworks and theories of truth. It raises critical questions about the limits of formal systems and the nature of self-referential statements, highlighting the complexities inherent in human communication. Philosophically, the liar paradox invites us to reflect on deeper issues regarding the nature of truth, the implications of self-reference, and the ethical dimensions of honesty and deception. It challenges us to consider how we understand and express our beliefs, as well as the assumptions we make about language and meaning. In summary, the liar paradox not only enriches our understanding of logic, but also encourages philosophical inquiry into the foundations of knowledge and reality. As we continue to grapple with these questions, the paradox remains a vital topic of discussion, reminding us of the intricate relationship between language, thought, and truth. The twin paradox is a fascinating thought experiment that illustrates the principles of Einstein's theory of relativity. At its core, it presents a scenario involving two identical twins, one of whom embarks on a journey through space at a significant fraction of the speed of light, while the other remains on Earth. As the traveling twin moves away from Earth, time for them slows down relative to their Earth-bound sibling. When they eventually return home, the traveling twin finds that they are younger than the twin who stayed behind. This counterintuitive outcome raises intriguing questions about the nature of time and our understanding of aging. The paradox challenges our intuitive perceptions of time, suggesting that it is not a constant, but rather a variable that can be influenced by speed and gravity. By exploring the twin paradox, we gain insight into the profound implications of Einstein's work and how it reshapes our understanding of the universe. Next, we will delve deeper into the specifics of Einstein's theory of relativity and how it underpins this remarkable phenomenon. Explanation of Einstein's theory of relativity. Einstein's theory of relativity, particularly special relativity, fundamentally changed our understanding of space and time. One of its key principles is the constancy of the speed of light, which states that light travels at the same speed, approximately 299,792 kilometers per second, regardless of the motion of the observer or the light source. This principle leads to remarkable consequences for how we perceive time and space. One such consequence is time dilation, where time appears to slow down for an object moving at high speeds compared to a stationary observer. In the context of the twin paradox, this means that the traveling twin, moving at a significant fraction of the speed of light, experiences time more slowly than the twin who remains on Earth. The concept of relativity of simultaneity further complicates our understanding, as events that seem simultaneous for one observer may not be so for another moving observer. Additionally, length contraction occurs where objects in motion are measured to be shorter in the direction of motion from the perspective of a stationary observer. To illustrate these effects, imagine a clock on the spaceship of the traveling twin. As they approach the speed of light, the ticking of their clock appears slower to the twin on Earth. This results in the traveling twin aging less during their journey, highlighting the paradoxical nature of time itself. Understanding these principles is essential for grasping why the twin paradox poses such a striking challenge to our conventional notions of time. Next, we will explore the specific scenario of the twin paradox and how these principles come into play. Scenario of the twin paradox. The twin paradox presents a captivating scenario that illustrates the effects of Einstein's theory of relativity. Imagine two identical twins. One stays on Earth, while the other embarks on a journey through space aboard a high-speed spaceship. As the traveling twin accelerates and moves away from Earth at a substantial fraction of the speed of light, something interesting happens. Due to time dilation, time for the traveling twin begins to slow down relative to the twin on Earth. While the twin on Earth experiences the passage of time as normal, the traveling twin's clock ticks more slowly. This means that during the journey, the traveling twin ages more slowly than their earthbound sibling. After a predetermined period, the traveling twin turns around and returns home. When they reunite, the astonishing outcome becomes clear. The traveling twin is younger than the twin who stayed on Earth. This outcome raises intriguing questions about the nature of time and aging. How can two individuals, born at the same moment, experience such a stark difference in their ages? The answer lies in the effects of high-speed travel and the principles of relativity. The twin paradox serves as a thought-provoking example of how our intuitive understanding of time can be radically altered in the context of relativity, challenging the very way we perceive reality. Consequences for understanding time. The twin paradox has profound implications for our understanding of time, challenging our intuitive perceptions and leading to intriguing discussions in both science and philosophy. One of the most significant outcomes is the realization that time is not a universal constant. Rather, it is relative and can be experienced differently based on an observer's speed and gravitational field. As demonstrated by the paradox, the traveling twin ages more slowly than the twin who remains on Earth, highlighting the concept of time dilation in a striking way. This paradox encourages us to reconsider our assumptions about aging and the passage of time. It suggests that time is intertwined with the fabric of space, forming a four-dimensional continuum known as space-time. The effects of time dilation are not just theoretical, they have been confirmed through real-world experiments. For instance, atomic clocks flown on airplanes or placed in satellites have shown measurable differences in elapsed time compared to those on Earth, providing empirical evidence for Einstein's predictions. Moreover, the twin paradox prompts philosophical inquiries about the nature of reality. If time can be experienced differently, what does that mean for our understanding of life, identity, and existence? Are our experiences of time merely subjective, shaped by our relative positions in the universe? These questions open a fascinating dialogue about the implications of relativity on our worldview. In summary, the twin paradox not only illustrates the complexities of time as described by relativity, but also invites deeper reflection on the nature of time itself, challenging us to rethink how we perceive aging, existence, and the universe. Next, we will conclude our exploration of this captivating topic and discuss its significance. Conclusion. The twin paradox serves as a compelling illustration of the principles of Einstein's theory of relativity, fundamentally reshaping our understanding of time and space. Through the scenario of two twins, we see how time dilation occurs due to high-speed travel, leading to one twin aging more slowly than the other. This paradox not only highlights the non-intuitive nature of time, but also emphasizes that our perceptions of reality are influenced by factors such as speed and gravity. By confirming the effects of time dilation through experimental evidence, the paradox reinforces the validity of relativity, encouraging us to think critically about our assumptions regarding time. It invites philosophical reflections on existence, identity, and the nature of reality itself, prompting us to consider how subjective experiences of time may vary across different observers. Ultimately, the twin paradox captures the imagination and challenges our understanding of the universe, demonstrating that time is more complex than it appears. As we continue to explore the implications of relativity, we gain deeper insights into the fundamental workings of the cosmos, reminding us that science often leads us to question and expand our understanding of the world around us. Schrödinger's cat paradox. Schrödinger's cat is a thought experiment that vividly illustrates the peculiarities of quantum mechanics and raises profound philosophical questions about the nature of reality. Proposed by physicist Erwin Schrödinger in 1935, the paradox involves a hypothetical scenario where a cat is placed inside a sealed box along with a radioactive atom, a Geiger counter, a vial of poison, and a hammer. If the Geiger counter detects radiation from the decaying atom, it triggers the hammer, which shatters the vial and releases the poison, ultimately killing the cat. However, if the atom does not decay, the cat remains alive. According to quantum mechanics, until the box is opened and observed, the cat exists in a superposition of states, both alive and dead simultaneously. This idea stems from the principle of superposition, which posits that particles can exist in multiple states at once until measured. The paradox highlights the challenge of reconciling the strange implications of quantum mechanics with our everyday understanding of reality. It forces us to confront the question: what does it mean for an object to exist in multiple states, and how does observation affect the state of a system? In this context, Schrödinger's cat serves as a critical lens through which we can explore the counterintuitive aspects of quantum theory and its implications for our understanding of the universe. Discussion of quantum mechanics. Quantum mechanics is a fundamental theory in physics that describes the behavior of matter and energy at the smallest scales, such as atoms and subatomic particles. It departs significantly from classical mechanics, introducing concepts that challenge our intuitive understanding of the physical world. One of the cornerstone principles of quantum mechanics is the concept of superposition, which posits that particles can exist in multiple states simultaneously until a measurement is made. This principle is essential to understanding the Schrödinger's cat paradox, as it illustrates how the cat can be considered both alive and dead until observed. Another key concept is quantum entanglement, where particles become interconnected in such a way that the state of one particle instantly influences the state of another, regardless of the distance separating them. This phenomenon has been experimentally verified and raises questions about the nature of information and locality in the universe. The probabilistic nature of quantum mechanics is also crucial. Unlike classical physics, where systems can be described with certainty, quantum mechanics provides only probabilities of finding a particle in a particular state when measured. This inherent uncertainty leads to various interpretations of quantum mechanics, including the Copenhagen interpretation, which suggests that a system does not have definite properties until observed. Schrödinger's cat encapsulates these ideas by forcing us to confront the implications of superposition and the role of the observer in determining the state of a system. It highlights the philosophical dilemmas that arise when we attempt to apply quantum mechanics to macroscopic objects, further complicating our understanding of reality in existence. As we delve deeper into these concepts, we can appreciate the profound impact of quantum mechanics on our perception of the universe. Examples of real-life applications. The principles of quantum mechanics, as illustrated by the Schrödinger's cat paradox, have found practical applications that significantly influence technology and various fields. One prominent example is quantum computing. Unlike classical computers, which use bits to represent information as either 0 or 1, quantum computers use quantum bits, or qubits. Qubits can exist in superpositions of states, allowing quantum computers to perform complex calculations at speeds unattainable by classical computers. This capability has the potential to revolutionize fields such as cryptography, optimization, and drug discovery. Another application is quantum cryptography, which utilizes the principles of quantum mechanics to create secure communication channels. Quantum key distribution, QKD, ensures that any attempt to eavesdrop on the communication will alter the quantum states involved, alerting the communicating parties to potential security breaches. This technology promises to provide unbreakable encryption methods, enhancing data security in an increasingly digital world. Quantum entanglement, a phenomenon closely related to the ideas presented in the Schrödinger's cat thought experiment, is also being explored for applications in quantum teleportation and secure data transfer. Researchers are investigating ways to harness entangled particles for faster communication and enhanced processing capabilities. Additionally, advancements in quantum sensors leverage quantum properties to achieve unprecedented precision in measurements, which can be applied in fields like medicine, navigation, and environmental monitoring. These real-life applications underscore the relevance of quantum mechanics beyond theoretical discussions, demonstrating how these abstract concepts can lead to groundbreaking technologies that reshape our understanding and interaction with the world. As we continue to explore the implications of quantum mechanics, we open new avenues for innovation and discovery in various domains. Conclusion: the Schrödinger's cat paradox serves as a powerful illustration of the complexities and counterintuitive nature of quantum mechanics. By presenting a scenario where a cat exists in a state of superposition, both alive and dead until observed, it challenges our conventional understanding of reality and forces us to confront the philosophical implications of observation and measurement. The principles of quantum mechanics, such as superposition and entanglement, not only redefine our understanding of the physical world, but also have practical applications that are revolutionizing technology. From quantum computing to secure communication through quantum cryptography, the concepts derived from this paradox have led to innovations that impact various fields, including information technology, medicine, and environmental science. As we continue to explore and apply these principles, we gain deeper insights into the nature of reality and the universe itself. Ultimately, the discussion surrounding Schrödinger's cat highlights the ongoing dialogue between science and philosophy, encouraging us to reconsider our perceptions of existence and the fundamental nature of reality. As quantum mechanics evolves, it promises to unlock new frontiers in both scientific understanding and technological advancement, underscoring the profound interconnectedness of these fields. Banach-Tarski Paradox. The Banach-Tarski Paradox is a fascinating and counterintuitive result in set theory and mathematics that challenges our understanding of volume and space. Formulated by mathematicians Stefan Banach and Alfred Tarski in 1924, the paradox asserts that it is possible to take a solid ball in three-dimensional space, divide it into a finite number of non-overlapping pieces, and then reassemble those pieces into two identical solid balls, each the same size as the original. At first glance, this seems impossible, as it contradicts our intuitive notions of volume and conservation. The paradox relies heavily on the axiom of choice, a fundamental principle in set theory that allows for the selection of elements from an infinite number of sets. This axiom enables the construction of the non-measurable sets used in the paradox, which do not conform to traditional geometric properties. The Banach-Tarski Paradox is not just a mathematical curiosity. It raises profound questions about the nature of infinity, the concept of volume, and the implications of abstract mathematical theories. It invites us to reconsider our intuitive understanding of physical objects and challenges the boundaries between mathematics and philosophy. As we delve deeper into this paradox, we will uncover its underlying principles and explore its implications for both mathematics and the broader understanding of reality. Explanation of the mathematical paradox. Imagine a solid ball, a simple three-dimensional object that we are all familiar with. Now, picture this. What if I told you that you could take this ball, cut it into a finite number of pieces, and then, using those very pieces, create not one, but two identical balls, each the same size as the original? This mind-bending idea is at the heart of the Banach-Tarski Paradox. To grasp this paradox, we need to delve into some fascinating concepts in mathematics. The first, and perhaps the most crucial, is the axiom of choice. This principle states that for any collection of non-empty sets, there is a way to select one element from each set. While this may sound straightforward, the implications are profound. The axiom of choice allows mathematicians to construct sets that do not conform to our usual understanding of size and volume. Now let's talk about those non-measurable sets. When we divide our ball, we're not slicing it into regular, well-defined pieces like wedges of a cake. Instead, we create sets that are abstract and defy conventional measurement. These pieces can't be assigned a traditional volume, which is where the paradox truly takes shape. So, how does this all come together? Starting with our solid ball, we divide it into a finite number of these strange abstract subsets. Using the axiom of choice, we can rearrange these pieces, not by stretching or altering them, but simply by rotating and moving them around in space. The magic happens here. We can reassemble these pieces in such a way that we end up with two identical balls, both the same size as the original. This revelation challenges our intuitive notions of volume and conservation. It suggests that, in the realm of mathematics, we can do things that seem impossible in the physical world. The Banach-Tarski Paradox serves as a reminder that mathematics often operates under rules that are vastly different from our everyday experiences. It invites us to explore deeper philosophical questions about existence, reality, and the nature of infinity. As we continue to unravel this paradox, we see that it not only fascinates mathematicians, but also prompts us to reconsider our understanding of the universe itself. The interplay between abstract concepts and our intuitive grasp of space opens a window into the mysterious and often counterintuitive nature of mathematics. Illustration of its strange properties. Now, let's dive into the intriguing world of the Banach-Tarski Paradox and explore its strange properties. Picture the original ball again, this solid, familiar object. When we talk about dividing it, it's not like cutting a pie into slices. Instead, we're engaging in a mathematical exercise that transforms our understanding of space. Imagine taking this ball and slicing it into a finite number of pieces. But these aren't simple geometric shapes. They are complex, abstract subsets created using the axiom of choice. Each piece is so bizarre that it doesn't conform to our usual ideas of size and volume. In fact, they're called non-measurable sets. This means that even though we can manipulate them mathematically, they defy any consistent way of measuring their volume. Now, let's think about what happens next. Once we have these pieces, we rearrange them. You might be wondering how we can take such peculiar shapes and reassemble them into two identical balls. This is where the magic of mathematics comes in. Through rotations and translations, imagine turning and moving these pieces around in space, we can transform our original ball into two complete copies. It's as if you've magically duplicated the ball, but without adding any material. This transformation challenges our basic intuitions. In the physical world, if you have one object and you cut it into pieces, you can't simply create more objects without additional material. Yet, in the realm of mathematics, particularly with infinite sets and the properties of these non-measurable pieces, the rules change. Now let's consider the implications of this paradox. It raises profound questions about the nature of reality. What does it mean for something to have a volume if we can't measure it in the traditional sense? The Banach-Tarski Paradox invites us to reflect on the nature of infinity and the limits of our understanding. It blurs the lines between the abstract world of mathematics and the tangible world we inhabit. As we ponder these strange properties, we begin to see how this paradox not only fascinates mathematicians, but also invites us to explore deeper philosophical questions. It challenges us to think about the very fabric of reality and how mathematics can reveal truths that seem impossible in our everyday lives. So, as you continue to engage with this paradox, keep in mind the remarkable interplay between mathematics, philosophy, and the nature of existence itself. Conclusion: the Banach-Tarski Paradox is more than just a mathematical curiosity. It is a profound exploration of the nature of infinity and the limits of our understanding. By demonstrating that a solid ball can be divided into non-measurable pieces and reassembled into two identical balls, the paradox challenges our intuitive notions of volume and conservation. This striking result hinges on the axiom of choice, a principle that allows for the existence of these bizarre, non-measurable sets. It serves as a reminder that mathematics operates under its own set of rules, often leading us to conclusions that seem impossible in the physical world. As we reflect on the implications of the Banach-Tarski Paradox, we find ourselves grappling with deeper questions about reality. What does it mean for something to exist if we can't measure it in traditional terms? How do abstract mathematical concepts inform our understanding of the universe? The paradox invites us to engage with these philosophical inquiries, bridging the gap between mathematics and the nature of existence. It encourages us to embrace the mysteries of the mathematical world, where intuition may falter, but imagination can soar. In the end, the Banach-Tarski Paradox not only enriches our understanding of mathematics, but also opens our minds to the complexities and wonders of reality itself. As we navigate this intricate landscape, we are reminded that the pursuit of knowledge often leads us to unexpected and astonishing discoveries. Bertrand's Paradox. Bertrand's paradox presents a fascinating challenge in the realm of probability theory. Formulated by the French mathematician Joseph Bertrand in the 19th century, this paradox illustrates the complexities and counterintuitive nature of probability, particularly when dealing with geometric contexts. At its core, the paradox revolves around a seemingly simple question. Given a circle, what is the probability that a randomly drawn chord is longer than the length of the side of the inscribed equilateral triangle? Intuitively, one might expect a straightforward answer. However, depending on the method used to define random, the answer can vary dramatically. This leads to different probabilities, revealing the paradoxical nature of our assumptions about randomness and probability. Bertrand's paradox serves as a crucial reminder that intuitive approaches to probability can often produce conflicting results. It highlights the importance of clearly defining conditions and methods when dealing with random events. This paradox not only challenges our understanding of probability, but also has significant implications for mathematical theory and applications. As we explore the intricacies of Bertrand's paradox, we will uncover the different interpretations that arise from various probabilistic methods. This investigation will deepen our understanding of the fundamental concepts of probability and encourage us to think critically about how we approach seemingly simple questions in mathematics. Discussion of probabilistic methods. Let's journey into the fascinating world of probability as we explore Bertrand's paradox. Imagine you have a perfect circle, and you want to draw a chord within it. Now, here's the intriguing part. How you choose that chord can lead to wildly different probabilities of it being longer than the side of an inscribed equilateral triangle. First, we need to think about what it means to draw a random chord. This idea isn't as straightforward as it seems. There are several methods to define randomness, and each method can lead us to a different answer. This is where the paradox truly comes to life. One common approach is the random endpoints method. In this scenario, you simply pick two random points on the circumference of the circle and connect them to form a chord. But here's the twist. This method gives us a specific probability that might suggest one outcome. For example, you might find that the chance of that chord being longer than the triangle's side is 1/4. Now, let's consider another method, the random radius method. Picture this. Instead of picking points on the edge, you select a random radius within the circle. Then at some point along that radius, you draw your chord. This method yields a different probability, perhaps 1/3, and shows us that our choice of how to define randomness can dramatically change the results. But we're not done yet. There's also the random angle method. Here, you select a random angle and draw a chord that is perpendicular to that angle at a point on the circle. With this approach, you might discover yet another probability, possibly landing at. Each method reveals a unique perspective on the same geometric scenario, illustrating the paradox at the heart of this mathematical puzzle. So what does this all mean? The disparity in probabilities highlights a crucial point. When we're dealing with concepts of randomness, clarity is vital. Each method operates under its own assumptions, and if we're not careful, we can easily arrive at conflicting conclusions. Bertrand's paradox invites us to reflect on the nature of probability itself. It challenges our intuition and shows us that the way we frame a question can significantly influence the answers we get. As we navigate through these different methods, we are reminded that mathematics is not just about numbers and formulas, it's also about the ideas and interpretations that shape our understanding of the world around us. In essence, the exploration of these probabilistic methods not only deepens our comprehension of Bertrand's paradox, but also enriches our appreciation for the complexities of probability theory. It encourages us to think critically about randomness and the assumptions we make, an essential exercise in both mathematics and life. Examples and their significance in mathematics. Now let's dive into some concrete examples of Bertrand's paradox and explore their significance in the broader landscape of mathematics. These examples not only illustrate the paradox itself, but also highlight the lessons we can learn about probability and our intuitive understanding of randomness. Consider the first example, using the random endpoints method. When we select 2 points on the circumference of the circle, we arrive at the probability that the chord will be longer than the side of the inscribed triangle. This result, while seemingly simple, raises important questions about how we perceive randomness. It reminds us that our intuition can sometimes lead us astray, especially in geometric contexts. Next, let's examine the random radius method. Here, we select a random radius and draw a chord based on that choice. This method gives us a different probability, 1/3. The variation in outcomes from different methods underscores a crucial lesson in probability: the need for precision in our definitions. It shows us that even a small change in how we approach a problem can yield significantly different results. Then there's the random angle method. By choosing an angle and drawing a chord perpendicular to it, we find yet another probability, 1 tau. This further reinforces the idea that probability isn't just about numbers, it's about the context and the assumptions we make. Each example serves as a reminder that mathematics is not always as straightforward as it appears. The significance of these examples extends beyond the paradox itself. They illustrate the complexities of probability theory and the importance of rigorous definitions. In a world where we often rely on intuition, Bertrand's paradox challenges us to think critically and to question our assumptions about randomness. Moreover, these examples have practical implications in various fields, from statistics to physics. Understanding how different methods can lead to different outcomes is crucial when designing experiments or interpreting data. It teaches us to be cautious in our conclusions and to recognize the potential for ambiguity in probabilistic situations. In essence, the exploration of these examples reveals the richness of probability theory. They not only illuminate the intricacies of Bertrand's paradox, but also encourage us to appreciate the deeper connections between mathematical concepts and the real world. As we navigate through these ideas, we are reminded that mathematics is a powerful tool for understanding the complexities of life, challenging our perceptions and expanding our horizons. Conclusion. As we wrap up our exploration of Bertrand's paradox, it's clear that this mathematical conundrum offers profound insights into the nature of probability and randomness. Through our journey, we've seen how different methods of defining a random chord in a circle can lead to varying probabilities, each revealing a unique perspective on the same problem. This paradox serves as a powerful reminder that mathematics is not just about arriving at answers, it's about the questions we ask and the assumptions we make. Each approach we discussed, the random endpoints method, the random radius method, and the random angle method, illustrates how subtle differences in our definitions can lead to dramatically different conclusions. This highlights the critical importance of clarity and precision in mathematical reasoning. Bertrand's paradox also invites us to reflect on the broader implications of probability theory. It challenges our intuitions and encourages us to think critically about the complex interplay between randomness and certainty. In a world where we often rely on instinct, understanding these nuances can significantly enhance our decision-making and analytical skills. Furthermore, the lessons we draw from this paradox extend beyond mathematics. They resonate in various fields, such as statistics, economics, and even philosophy, where the interpretation of data and the formulation of theories depend heavily on how we define randomness and probability. In conclusion, Bertrand's paradox not only enriches our understanding of probability, but also prompts us to engage with deeper questions about the nature of reality and our perception of it. As we continue to explore the intricacies of mathematics, let us carry forward the insights gained from this paradox, remaining curious and open-minded in our pursuit of knowledge. Through this lens, we can appreciate the beauty and complexity of the mathematical world around us, inspiring us to delve even deeper into its mysteries. Gibbs Paradox. The Gibbs Paradox is a fascinating concept in thermodynamics that highlights the complexities of entropy and the behavior of gases. Named after the American physicist Josiah Willard Gibbs, this paradox arises when we consider the mixing of identical particles in a gas and its implications for our understanding of entropy. At its core, the paradox presents a puzzling scenario. When two identical gases are mixed, Classical thermodynamics suggests that the entropy of the system should increase. However, if these gases are truly identical, the question arises, should we treat them as distinct entities? The challenge lies in reconciling this apparent contradiction and understanding how it affects our calculations of entropy. Historically, Gibbs introduced this paradox in the context of statistical mechanics, aiming to bridge the gap between microscopic particle behavior and macroscopic thermodynamic properties. The paradox serves as a critical point of discussion, prompting scientists to rethink the nature of particles and the role of indistinguishability in thermodynamic processes. As we delve deeper into the Gibbs Paradox, we will explore the thermodynamic aspects that underpin it and examine how this paradox influences our understanding of entropy. This journey will reveal not only the intricacies of thermodynamics, but also the profound implications for the foundations of statistical mechanics and our grasp of physical laws. Explanation of thermodynamic aspects. Imagine you have two containers, each filled with the same gas. You open a barrier between them and the gases mix. At first glance, it seems straightforward. When they mix, the disorder increases and so does the entropy of the system. But here's the twist. If the gases are truly identical, can we really say that mixing them leads to a change at all? To unravel this mystery, we need to dive into some fundamental principles of thermodynamics. The second law of thermodynamics tells us that in an isolated system, entropy can never decrease. It can only stay the same or increase. This law is a cornerstone of our understanding of how energy and matter behave over time. Now, let's think about those identical gases. In classical physics, we treat particles as distinguishable. When you mix them, it seems logical to conclude that the system's entropy increases because we have more possible arrangements of particles. However, if these particles are genuinely identical, this raises an intriguing question. Why should mixing them result in an increase in entropy? This is where the paradox deepens. Quantum mechanics teaches us that identical particles are fundamentally indistinguishable. If you swap two identical particles, you haven't changed the state of the system at all. It's as if they were never distinct to begin with. This realization is pivotal because it alters our understanding of what it means to calculate entropy. Now let's bring in the perspective of statistical mechanics, which is where Josiah Willard Gibbs made significant contributions. He showed us that by acknowledging the indistinguishability of particles, we can correctly compute the statistical weight of a system. When we mix identical gases, we need to adjust our calculations to reflect that swapping particles doesn't create a new state. This adjustment is crucial. It helps us avoid the miscalculation of entropy that arises from treating identical particles as if they were distinct. In essence, the Gibbs paradox serves as a reminder of the complexities involved in thermodynamic calculations and the necessity of a nuanced approach. So, as we explore the implications of this paradox, we uncover not just a quirk of gas behavior, but a profound insight into the nature of entropy itself. It challenges us to rethink our assumptions about particles, disorder, and the laws that govern the physical world. Through this lens, we gain a deeper appreciation of the intricate dance between thermodynamics and statistical mechanics, revealing a more complete picture of the universe around us. Influence on understanding of entropy. As we delve deeper into the implications of Gibbs paradox, we find ourselves at the heart of one of the most fascinating concepts in physics: entropy. This paradox not only challenges our understanding of how entropy behaves, but also reshapes the way we think about disorder in physical systems. At its core, entropy is a measure of uncertainty or disorder within a system. In classical thermodynamics, we often think of entropy as a one-way street. When systems evolve, they tend to move toward greater disorder. This is where the paradox becomes intriguing. When we mix identical gases, classical theory suggests that the entropy should increase. However, if the gases are indistinguishable, does the idea of mixing even apply? This question leads us to reconsider the very nature of entropy. Gibbs Paradox forces us to recognize that our traditional definitions may not hold up when we account for the indistinguishability of particles. If we treat identical particles as unique, we end up inflating the calculated entropy, suggesting a level of disorder that doesn't actually exist. Through the lens of statistical mechanics, we begin to see a clearer picture. By acknowledging that identical particles are indistinguishable, we adjust our calculations to accurately reflect the system's true state. This adjustment is not just a technical correction, it fundamentally alters our understanding of how entropy operates in real-world scenarios. Moreover, the paradox has broader implications for various fields, from chemistry to information theory. In chemistry, for instance, it influences how we interpret reactions and mixtures, especially in cases where identical species are involved. In information theory, it reshapes our concepts of uncertainty and information content, emphasizing the importance of context in defining these terms. Ultimately, Gibbs Paradox serves as a crucial turning point in our understanding of entropy. It reminds us that our intuitive grasp of disorder is not always sufficient. We must engage with the underlying principles of statistical mechanics to fully appreciate the complexities of entropy and its role in the universe. As we reflect on these insights, we begin to see entropy not merely as a measure of disorder, but as a fundamental aspect of physical reality, one that connects the micro and macro worlds in profound ways. This deeper understanding encourages us to keep questioning and exploring, as it is through such inquiry that we can unlock the mysteries of the universe. Conclusion. In wrapping up our exploration of Gibbs Paradox, we recognize its profound impact on our understanding of thermodynamics and entropy. This paradox challenges us to rethink the way we approach the concepts of mixing and disorder in physical systems. Through our discussion, we've seen how the assumptions we make about particles, specifically their distinguishability, can significantly alter our calculations and interpretations of entropy. By delving into the principles of statistical mechanics, we've gained insights that allow us to reconcile the apparent contradictions presented by the paradox. The lessons learned from Gibbs Paradox extend beyond the realm of thermodynamics. They inspire critical thinking in various fields, encouraging scientists and researchers to question their assumptions and refine their models. Whether in chemistry, physics, or even information theory, the implications of this paradox resonate, reminding us of the intricate connections between different areas of study. Ultimately, Gibbs Paradox serves as a gateway to deeper philosophical questions about the nature of reality and our understanding of the universe. It invites us to explore the complexities of entropy, urging us to look beyond surface-level interpretations and engage with the fundamental principles that govern our world. As we continue our journey in the realms of science and mathematics, let us carry forward the insights gained from this paradox, remaining curious and open to new ideas. By embracing the complexities of concepts like entropy, we can further appreciate the beauty and intricacy of the universe, driving us to explore even deeper into its mysteries. And now we have reached the end of the video. I won't say goodbye. See you next time.